Hello everyone, welcome to this video. In this video, I am posing you this question that can we calculate the inner automorphism group for D6 without actual computation, right? So I have here presented an example of such kind where by the theorems and results that we have studied, we are able to tell about this inner automorphism group of D6. What is D6? It is a dihedral group, right, or of order 12 that you know. So before moving forward for this inner automorphism group of D6, let's see a general result for Dn. For that we'll be requiring the center. So let's see what is the center of the general dihedral group Dn. So I say that it is when n is even, so that means for D2, D4, D6, D8 and so on, we have R0 and R180 as two elements present in the center, and whenever we have it as odd, in that case only the identity element is present in the center, right? So let's first of all see this thing here. So you know, rotations in Dn, they are represented when you divide the number of sides. In fact, this n 360 with this n, right? So that many rotations you get. So and moreover, you know, rotations commute with rotations. When if you perform one rotation and then second rotation, or you perform second rotation and then one rotation, so both will give you the same result. So therefore they commute with each other. So because in dihedral group we have two kind of elements. One is reflections, another one is rotations, right? So for rotations we are clear they commute with each other. What about reflections? Do they commute with each other? And what about reflections with rotations? Do they commute with each other? If that is the case, we wanted to know which all elements commute with all the other elements here, right? Rotations commute with rotations. Does rotation commute with reflections as well? Now let's check this thing, whether a rotation commute with the reflection or not. For that we consider capital R to be a rotation and capital F to be any reflection in Dn, right? So that means, you know, a rotation followed by a reflection is a reflection. That I have told, that thing we have solved in the question answer part of in the question answer playlist of group theory. You can check from there, a detailed description is taught over there, right? So rotation followed by a reflection is a reflection, that we know. And moreover we know the inverse of reflection is a reflection, right? You can check there, I have given you a detailed description of this. So here you see this reflection would be equal to its inverse, right? And by the sock-shoe property you can invert the order F inverse and R inverse, right? And reflection inverse, because this is the reflection, that is the reflection itself, which is F, so FR inverse. So from here you obtain RF is equals to FR inverse, right? Now we want them to commute. Why? Because if that is the case, then rotation would be present in the center. Because we know rotation commute with other rotations, right? And if this rotation also commute with reflections, then rotations is present in the center, because in center we have all the elements which commute with all the other elements of the group, right? So for them to commute, what do we require? Instead of this R inverse, if we have RF is equals to FR, then we are through, right? So that means we are looking for only those rotations for which we have this property. And whenever our n is even, in that case, when you divide 360 by some even number, you will definitely get 180, right? 180 would surely be there. So in that case, and you know, R180 into R180 in any case, that is R360 basically, and which is R0. So you see here R180 inverse is R180, and moreover R0 into R0 is R0, so that means R0 inverse is R0. So this property is followed by only two elements when we have n as even, and when we have n as odd, R180 is not present there. If that is not present, so only R0 is present. So that means whenever our n is even, we have only 2 elements present in the center, and when n is odd, we have only one element, which is the identity element, present in the center, right? And so from here, because 6 is an even number, hence the center of D6 would contain exactly 2 elements, which are R0 and R180. Correct. Once you know the order of the center, you can very easily compute the order of the factor group created by this center, right? So by the Lagrange's theorem, it would be equal to the order of the group divided by the order of the subgroup. Order of the group, you know, is 12. It is 2n, n is 6. And here we have, you know, the order is 2. Hence, the order of factor groups comes out to be equal to 6, right? If you know the order of this factor group, and it is 6, which could be written as 2 into 3, right? 3 is a prime number, so it could be written as 2 times of some prime number. So by this result, we can clearly say whatever is our group is this one, D6 divided by the center Z of D6. This group would either be isomorphic to Z2P or DP. So this would either be isomorphic to Z6 or it would be isomorphic to D3. Correct, according to this result here. That is what I have written over here. Now in the first case, if we take this inner automorphism group of D6 to be isomorphic to Z6, in that case, because you know Z6 is a cyclic group, right? Hence this would also be cyclic. If this is cyclic, so because we have studied about this result that inner automorphism group of G is isomorphic to the factor group created by the center, hence D6 by over the center of D6 would also be cyclic, correct? If this is cyclic, then again by the result that we have studied for a group and its center, that the factor group constructed by this center is cyclic, then G is abelian, right? Now we are saying this is cyclic, so that means this D6 should be abelian. So we are saying this D6 is abelian according to this result. And D6 is abelian, what does it mean? It means that all the elements commute here. However, this is not possible in D6, correct? Hence we cannot have the inner automorphism group of D6 isomorphic to Z6. This cannot be there. So the only choice available is this. So once you know the structure of D3, right, which is the symmetries of a triangle, you automatically know the inner automorphism group of D6. Right, that's simple as that. So you see, without actual computation, we can very easily reach to the conclusion that this inner automorphism group of D6 is basically isomorphic to D3, in which you know we have 3 rotations and 3 reflections, right? So I hope you understood this question and concept well. Well, that is it for this video. Thank you for watching.